Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. Today in the podcast, we're talking about A5, a discrete global grid system similar to S2 and H3, but with higher accuracy and lower distortion. And to talk us through how it all works is Felix Palmer. So I had the privilege of catching up with Felix at 2025 FOSS4G in Auckland, and this podcast was recorded there. Hey, Felix, welcome to the podcast.
Hey, it's great to be here.
Yeah, I'm really stoked that you are interested in coming along and talking to me. I've just listened to your talk. We're here at FOSS4G 25 in Auckland. You were talking about something called A5. Fascinating stuff. I'm really looking forward to sort of diving into some of the details there. Is it correct you're a maintainer of DGGL?
Yeah, that's true. I've been maintaining DGGL, not just me, for the last 4 years. And DGGL is a visualization framework on the web. So it's written in JavaScript and it gets used with a lot of big data visualization. So if something like a Map Libre or Google Map app can't handle over like 1 million points, then people often will reach for DGGL. Or if they want to do something a bit more interactive or interesting, then they'll use DGGL.
But before we start talking about global grid systems, how did you get involved in that? What was your path to?
Yeah, the path was, I guess, a complicated one. So my background, I studied physics at Oxford. So I'm more coming from the mathsy side than programmer or geospatial side. But I always liked this more kind of like real world visual side of physics. Like when I was a teenager, I tried to build like an electric organ. And after I finished studying physics, then I actually ended up working in software, but I always liked these visual things. So as a side project, and now it's quite a long time ago, I started making this like visualization framework called Procedural, which was something similar to like Google Earth. So you basically visualize a 3D landscape in the browser. And after some time, I finished with this project and moved on to working in a way like a related project in terms of technology, but a very kind of different one. And that was this kind of DGGL. So through some twists and turns, I've kind of found a niche for myself in this sort of like high performance graphics programming, but on the web. So when I tell people that I'm kind of doing web pages or a web developer, then they might say like, oh, so can you make like a WordPress site for me? And it's like, yeah, it's not quite the same thing. So
Yeah. That is a bit of a complicated journey to get here. I don't want to bury the lead too much, but just so the listeners know, A5 is a global grid system. And before we talk about the specifics of that and why we might choose that over other ones, would you mind just giving me the 101 of global grid systems? What are they? What do we use them for? And why should we care about them?
Yeah, sure. So often in just data analysis or in geospatial data analysis, we want to divide some kind of region up into equal size or near equal sized cells. Say we kind of want to have an understanding of where people are living or what the crime rates are like, then often we need to have some kind of bucketing systems. And as humanity, then we've made things like zip codes for this. But for science and analysis, it is more useful to have like a general system that can work across the whole world. Now, if the world was flat, then this would be pretty easy to do because we could just subdivide it like a chessboard or a honeycomb and we'd be done. But it's more complex because the world is a sphere and it's not even quite a sphere. It's like a slight ellipsoid. And if you try and divide it, then you can do it in one local region. It's not hard to divide a city into city blocks. But as you extend this further and further from the city, then you end up with some kind of distortion or the cells not meshing perfectly together. And actually, this same problem is one that you run into, say, if you're looking at the night sky and you want to have a way of representing patches there. It's also kind of like, how do I make a sphere into a flat surface? Or if you fly a space probe somewhere and you want to sample a planet, then you need to have a way of like storing that data. And actually, this was one of the earliest kind of grid systems that was basically kind of, I think it's called COBE. And that was actually like a sensor on a spacecraft sometime in like the 70s. So there's a long kind of history of just trying to, what at the heart of it is this kind of mathematical problem of you can't sort of, it's not like squaring a circle, but it's like flattening a sphere.
And just to be clear, we're talking about using them for analysis as opposed to navigation.
Yeah, it's generally for some kind of analysis. Yeah. So It's generally like kind of like data science. So one option is like for analysis. So say you just want to have an understanding of just where people are living in the US, then you want to divide it into cells. But if you want to do something like draw a connection between like two variables, so say like income and I don't know, temperature or something like that, then you might have like two data sets in two completely different formats, and you have no way that you can do some kind of regression. And these grid systems provide you a way of dividing the world into equal cells that are in a fixed like coordinate system. And then if each of them has an identifier, then you can join on those using a very, very simple SQL query. So it's basically a way of reducing the dimensionality of quite a complex system, which is our whole Earth, to one dimension. Just basically everything is just a cell and it's just got one ID.
So a couple of different systems that I think a lot of people might have heard of before would be S2, H, and H3.
Yeah, so these are definitely not the first systems, but they are those which have become very widely used. So S2 was developed at Google, and they actually use it under the covers in a bunch of their services. I mean, I'm not even sure how much of it is known in public, but for example, in like BigQuery, if you want to speed up a geospatial query, it is using S2 underneath the covers. And S2 is quite nice because it's easy to describe and understand. And the way you can think of it is that you take a cube and you pretend the cube is the Earth. So it's a pretty kind of rough approximation. On the side of every cube, you put like a chessboard, and that's kind of your indexing system. And this chessboard can be made smaller and smaller and smaller if you want to have smaller cells, or they can be big if you want to deal with kind of like big data. The problem is that, I mean, the Earth is not a cube, so you can ask, like, how do you get around that? And this is sort of like the key issue with these grid systems is that you have this projection step where each of the flat surfaces of the cube gets projected with a certain projection to the sphere. And depending on which projection you choose, then you're going to get different behaviors. It's exactly the same as just map projections in general. For different use cases, you're going to use a different projection, and there's definitely no perfect projection. You could argue there's just many sort of, bad or imperfect projections, or they have like one specific use case that they are good for, and then they fail in others.
Yeah. Just going back to what you said earlier, you said dividing the world up into equal squares, or in the case of S2, but not equal distance squares. Is that correct?
Well, it depends which squares we're talking about. So when it's on the surface of this cube with S2, then they are all equal. But in projecting them, then they become unequal, and they also have an angular distortion, so they become diamond shapes rather than squares. So it's like a double shift. And it's the same as with map projections. If you project something to a flat, like a flat map, then Greenland starts looking huge. It starts looking the shape of Africa, even though in reality, it's completely just different. Yeah.
In that scenario, where do we see most of the distortion? Is it around the edges of the sides, or?
So it's at the sort of spikes, so at the vertices. So if you kind of think about like what object you would like to be hit on the head with, then a ball is probably the best one, right? Like that's not going to hurt. Whereas a pyramid is going to be pretty bad, a cube is going to be pretty bad. But if you are going to be hit on any bit of the cube, you'd prefer the flat surface. So when you kind of inflate that cube, so to speak, with the projection, then it's the regions which were nearest to the spike, the corner, which get stretched out. And it kind of makes sense because they look nothing like the cube, whereas the bits in the center, well, those are, pretty close to the sphere.
Have you ever considered a career in teaching, communication or something? Because you're doing a fantastic job of explaining a very, very complex subject. It's awesome.
Yeah, thanks. Yeah.
Okay, S2, great. Well, what about, there's another one out there, you might have heard of it, H3.
Yeah, so this was one that was brought out by Uber, I think maybe 8 years ago or something. And they were building on ideas that have been around since the 90s. But one thing that they did very well was provide an ecosystem. So if you wanted to use this system of theirs, which I'll get onto, then you could get a JavaScript library, you could get a nice visualization tool. It was integrated into various database systems. So in part because of this ecosystem, this has actually become a very popular tool to use in this space. Now, H3 is a little bit more complicated to explain if you're not a nerd into platonic solids, but it kind of becomes, it's the same kind of like idea. So we start with a shape called an icosahedron, which is like, it looks quite close to a sphere. Rather than being built up from square sides, it's built up from triangles, and it has 20 such triangles. And you can kind of imagine it being like a less spiky shape. So it's actually a closer approximation of the sphere in that sense. And that property means that when you then do the projection, then you're not getting anywhere near as much angular distortion. And this is one of the reasons that I think people like H3 is that it actually looks quite nice. Like the hexagons that are perfect hexagons on the face of the icosahedron, then they almost are perfect hexagons when you project them onto a sphere. They're not, but at first glance they are. Whereas with S2, then you look at it and it often just looks a bit off. Now that's not to sort of like hate on S2. It's just that for visualization, it's just not as pleasing. But for certain use cases, you don't care about visualization, like optimizing a database.
You're doing amazing. Okay, so I'd really like to have the 101 on A5, and then it'd be super interesting to compare and contrast these things a bit, so we get an idea of the strengths and weaknesses.
Mm-hmm. So now that we know what kind of S2 is and what H3 is, then we're basically saying, okay, we're starting from some approximation of the Earth in the form of a polyhedron or a platonic solid, and we are sticking some tiling system on each face and then projecting it to basically in the end up with a sort of collection of cells that subdivide the world in some nice way. So A5 starts with the dodecahedron, not an icosahedron. So this is a shape that starts, has 12 pentagonal faces and is actually even less spiky in my parlance than the icosahedron, which means that when you do the projection, then you get less angular variation. And in a way, you can use it for many of the same things you could use H3. So say you want to bucket some kind of data, then these libraries often have a function which is something like longitude, latitude to cell. So you give it a bunch of points, it converts it into cells, then you can aggregate from this kind of cell ID, and then you can see, oh, okay, this is the cell that has the highest density. There is kind of like something's interesting happening. So you can do that same thing with A5 in exactly the same way that you could with H3, basically.
So why would I then use A5 over H3?
So one of the choices that H3 made when it was being developed, and remember, this was a system that was built by a ride-sharing company that was trying to match drivers to riders, essentially, and that was their use case. That was their kind of success criteria. I don't think they were planning on making a system that would be used widely. I mean, I'm sure they had a very good kind of open source mentality, but I don't think that's why they did it. They did it because they were trying to solve a problem of their own. The reason I say this is that for that particular use case, it doesn't actually matter if the cell sizes are not exactly the same. So when they developed the system, then they chose a projection, which means that the hexagons, once projected to the sphere, don't have exactly the same size. There's roughly a factor of 2 between the smallest one and the largest one. And this comes from basically this inflation of this shape from the icosahedron to the sphere. Like some places are getting stretched and some are not getting stretched. So A5 uses a different projection system, which maintains exact equal area. And it even considers the fact that the Earth is not spherical, but ellipsoidal. So what it means is that when you run this kind of workflow, which has like a conversion from longitude, latitude to cells, then the cells that you get out are all exactly the same size. And you then don't have to worry about that in your analysis. And for certain types of analysis, then that might matter. And for others, it might not. If you're just trying to match like a driver to a rider, then you don't really care. But an example, and I do actually see quite a lot of people doing this, is they might take a bunch of point data, like, I don't know, population density. They convert it into H3 cells, and then they apply a color ramp depending on how many people you had in each hexagon. But that's just not valid because each hexagon has got a different size. So you shouldn't be coloring them without normalizing them. Like one way that I actually have of thinking about this is the units are different. So if you imagine that you're doing measurements in, say, London and Paris, then in London we use miles for distances, and in Paris we use kilometers. I say we, I mean, I have nothing to do with Paris, but sure. And you then can't compare like with like. Like if you're going to be comparing like people's commute and you say in London it's 10 miles and in Paris it's 10 kilometers, therefore it's the same, then it's kind of obviously wrong. But the difference between a mile and a kilometer is even less than 2x. But this is kind of what you can end up doing inadvertently with a non-equal area system like H3.
Now, I realize you've just talked about this moments ago, but you had this brilliant example where I think you used Buenos Aires. Yeah, and because it was closer to the Pentagon in H3, the distortion was greater. So
yeah.
Would you mind talking me through that one, please? That was really interesting.
I mean, so having just given a talk with the aid of a projector, then I appreciate how difficult it is to do it without the visual side. If people are listening along and they have access to their phone or computer, I would say check out the a5geo.org website, because there's a bunch of visualizations on there, not just showing what you can do with A5, but kind of how it works. And one in particular is really a good aid in explaining this issue.
I'll be sure to link to all this in the show notes so people can easily find it.
So to explain the kind of Buenos Aires problem, then if you imagine a football or a soccer ball, then that's actually got exactly the same configuration as this icosahedron that we've been talking about. If you look at it, then it has 12 black pentagons on it, and in between the panels are white hexagons. So for exactly the same reason that H3 has these pentagons, then a football has to have them, because if it didn't, it wouldn't be round. And if you look at a football, you can see that the pentagons are a little bit smaller than the hexagons, and it kind of intuitively makes sense because the edge lengths are the same, but one of them has only got 5 sides and one has got 6. So it's kind of like logically going to be a bigger shape. Now, in constructing the H3 system, then they had to make a choice of like, how do we orient the world? Where do we put these pentagons? And they did a pretty clever job of this. They basically put them mostly in the sea. So you don't sort of hit the pentagon, but it's not just the pentagon that's small. Like the closer you get to it, the smaller it gets. And if you look at the pentagon that's near Buenos Aires, it is actually quite close to it. So what is happening there is that is one particular location where the cells are getting very, very small. And then if you compare it to somewhere in like the middle of the US, for example, I think, then there it is quite big. So if you end up doing an analysis, and I actually have an example of this directly on the site, I'm comparing Oslo and Malta in Europe, then these two locations, then within each location, the cell sizes are the same. But if you compare between them, then one is basically double the other. And then you can get this problem that when you're trying to compute the density, that it doesn't come out the same.
Yeah, so I agree that it's difficult to explain without the visual side of it, but you did a great job. And again, I will link to this in the show notes so people can go and check it out for themselves. And to be fair, you have a bunch of other really interesting and incredibly visual examples on the website, which are worth looking at. Really interesting comparisons. I also want to iterate, make sure that people understand you're not dunking on H3 or anything else. This is purely, we're using comparison to help people understand the difference between them, the pros and cons, if you will. This is going to be a hard question, I think, but I'm going to try for it anyway. When I think about choosing a global grid system, what key metrics should I be looking at? And this might depend dramatically on what I'm trying to do, but can you give us any sort of guidelines there?
So one is obviously this equal area aspect that we've already talked about. Another is like what range of cell sizes can you get? And this is kind of relevant both at the sort of high level and the low level. So I've actually had some people who had some raster imagery and they said, can I convert it into H3? Well, the answer is no, because a H3 cell at the sort of greatest resolution is 1 meter. So if you want to represent like something smaller than that, it's just not going to work. It's going to be very, very blurry. Now, again, H3 was not designed to store raster imagery, but if that's what you want to do, then it's not going to work.
Without resampling the imagery?
But even if you resample, then your smallest cell is going to be 1 meter. So if in that cell you want to kind of have like some text on a road, it's just going to get completely blurred out. Now, by comparison, S2 then goes down to 1 square centimeter. So you can do much, much more with that. With A5, you can do even a little bit better. So it goes to one more level than that. So it's roughly 30 square millimeters.
Wow.
So it really goes to something very, very small. And when I talk about like going down to a certain level, that means going down and being represented by a single 64-bit integer. Because if you can represent it with like a sort of a bigger integer, then that's kind of cheating. Like that's not impressive. So these systems generally try and output 64-bit integers because those can be used as keys in databases. And then depending on how kind of granular you want to go, then you might be able to represent some kind of outline or area up to the accuracy of centimeters rather than meters. So that's kind of like one end. The other one is maybe a bit subtle, but you have to think about what is the biggest cell that you can have. So in the S2 system, if you remember it was built as a cube, then you have kind of 6 cells, which are your kind of like resolution 0 cells, which are pretty big. They cover continents. And if you imagine sort of dividing your data into those cells at the lowest granularity, then that's going to have sort of 6 buckets. With H3, you start with 122, which might sound like a surprising number. I always forget why it's exactly like that, but it's something to do with the number 12. That actually can become an issue. Say you have like a web map and you want to, say, download your data in tiles that are grouped by H3, which is kind of natural if you're working with H3 data. If you want to load the whole world, you have to do 122 requests, if that's your kind of key on your URL. So it's kind of a bit unfortunate that the hierarchy of H3 doesn't go all the way up to the whole world. And with A5, then I've chosen to have the hierarchy go all the way up to the whole world, not in quite the same way as with S2, but there basically is a concept of the world as like the sort of global cell, and you can then divide that up into the dodecahedron faces, and then you can keep going down and down and down and down and down. Everything has a child, everything has a parent, all the way down to 30 square millimeters.
Wow. Could you tell me a little bit about the ecosystem around this? I think one of the reasons why H3 has been so successful, if you think about just distribution of it, how many people know about it, how many people are using it, is probably because of the ecosystem. It's easy to use.
Yeah, undoubtedly. And without any kind of implication that this is H3, then there's many examples where the worst technology wins out because it gets like greater adoption.
Distribution, yeah.
Yeah, and I mean, sometimes I kind of have to, shows my age a bit, but I have to laugh at how we used to have like records which were high fidelity, and we'd have like systems that we would play them and people would buy speakers and sit down and listen to music. And now people just, listen to low resolution music from YouTube on a phone. And this because it's easy, and it's very, very simple to be distributed. You don't have to go to a shop. You don't have to buy anything. So sometimes the easiest solution is there. And it's to do with reducing friction. So I think Uber here and then the community around it has done like a great job to explain to people what they can do with such a system and made it available in many, many different languages. So you can have a workflow where you in your database, you can import some kind of H3 integration. You can process your data and save it to a file. Then you can import it in Python and run analysis on it and get more H3 cells out. And then if you want to visualize it, you can just take those and put them into, QGIS or DGGL or many other kind of libraries. It's strong because all of these things together contribute more. And if you just had like one library, then like technically, yes, you could do this analysis, but it becomes so hard that you can't expect someone to kind of build all these tools and tool chain for themselves. And actually, one of the first things that I had a conversation with one of the other DGGL maintainers when I was first releasing this, and she said if you want people to use this, you have to give them really great tooling. And she should know she also worked on Uber and from one of the kind of original maintainers of a DGGL. So in a way, yes, you need to have some something kind of that's mathematically and structurally solid, but it's not going to matter unless you can get it in the hands of enough people and make it easy for them. So with this in mind, then I had this strategy of saying, okay, I've written this in TypeScript. That's because that's what I know, and I do visualization. That's not what most people want they're going to want Python because that's the language for data science, and some kind of high performance language. So the cool one these days to choose is Rust, of course. And this was actually kind of interesting because here I really leaned on the tools that we have this year, all these kind of LLM and agent models, in particular Claude Code. Then it helped me like translate from first JavaScript to Python, and Python is a language that I know. And with the aid of very kind of granular tests, because if you think of like what this code base looks like, it's mostly kind of low-level maths. I've tried to minimize the dependencies. There's basically zero. So it's just like all the native code. And it then means that you can really do this kind of true test-driven development where you have a bunch of inputs and outputs, which can be saved as JSON files. And an LLM can iterate and really understand, I have got it right. Like it's not just kind of guess that it has it right. You can verify it.
I'm just sitting here listening to you and thinking, I wonder if LLMs are going to change the way we distribute stuff. You know, the speed at which things can be distributed just because of exactly what you're talking about.
Yeah.
You can make tools faster, more tooling, more better, more distribution, people using.
I mean, this was actually kind of a conscious choice on my side. So if, again, I'm going to compare myself to H3, all of these different systems that they have, then it's important that they're consistent. Like it's not good enough if they're most of the time correct, and sometimes they give you a different cell. That defies the whole point. So the approach that they have taken is they've written it in, I think it's C or maybe C++, and then they have bindings in the different languages. So if you are pulling in the JavaScript library, then the actual maths is not running in JavaScript. It's running in a compiled binary somewhere. The same is true for Python and a bunch of other languages. Now, in a way, this is very clever because it's cool that you can somehow invoke compiled C in the browser. What I thought it was not so good for is if you want to build an ecosystem, then as a JavaScript developer, if you tell me that the API itself is written in C and I have to install some toolchain, then I'm like, I don't know how to do that. Like, I don't even know how to write this code. So I took this approach, which I coined a term for, and which I have on the website. It's called polyglot mirroring. You can tell me what you think of that. It sounds fancy.
Just rolls off the tongue.
It rolls off the tongue.
Love it.
I think it makes sense, right? I'll explain it. Where rather than having like one core language and bindings that go to it, you have a collection of languages which are sort of equal, and you mirror between them. So it's like the polyglot and then the mirroring, and you use LLMs to keep them in sync. So if I make a change in one language, I should just be able to say, hey, Claude, port it to Rust and port it to Python. And this basically works. And it essentially means that if someone in the future wants to make an improvement to it and they're a Rust developer, they can do it in the Rust side, and then it can be ported back. So we can end up with a code base that's like multilingual at the same time. And if the structure is similar enough, then this is the thing that the LLMs are super good at. They kind of recognize patterns. They don't understand what's going on, but they're super good at going like, you did this there, and that's how that was done in Rust, and this is how you multiply two vectors in one language, and they kind of transfer these things across. And for me, what was a real kind of wow moment is that I did the TypeScript version, then I did the Python version, and a kind of nice side effect of doing this port was that there was a bunch of precision issues that got filtered out because the different languages were slightly rounding stuff. So it actually improved the code base to write it twice. But the real wow moment was like when I came to Rust, and I've never written a line of Rust code in my life. And I was like, I'm going to have to find someone to do this, and then I'm going to do it. And but I thought, I'll just see if Claude can do it. And I already have like 2 code bases. I already have a bunch of tests, and I just like set it off running. Often it ran out of credits, so I'd come back in the middle of the night and just press continue. And after a week of just doing this, it had a working code base with like a few bugs, which I then managed to fix. And generally speaking, I didn't have to go and write anything manually. So it was actually able to produce a true translation, which now with some help from actual people who understand Rust, they've managed to make faster than the original TypeScript. And this to me, like sometimes when you think about like why projects succeed or companies succeed, it's like, why now? Like what has changed? And like this year, it's very obvious that what has changed is that you have these tools, which for next to no money, you as a single developer can use to kind of like have a team of people helping you. So for certain things, then I think these language models are just like amazing, and they kind of let you do something which would just not been possible a year ago.
Fascinating. I've never heard of that approach before, but when you talk me through it makes a lot of sense. I think too, though, a lot of people will hear that and go, he's using LLMs, they hallucinate, there's bugs all through the code. What would you say to those people?
I mean, the functions that they are kind of translating, then they're very often just some kind of numeric input and numeric output. And a lot of time was spent trying to make sure the precision was right. So, I mean, many, many painful hours, because you're essentially trying to make a model of the Earth. And if your maths means that a point moves by a fraction of a millimeter, then that's not good enough. So like that really is at the kind of limits of what floating point can represent. Then if you have a bunch of tests which kind of verify a bunch of inputs and outputs, and you have things like, I want to take a location and convert it into a cell and then convert the cell back into the location, it's very easy to just generate 1,000 of these and just test that they work and then be pretty confident that it works.
Yeah.
Because it's like a very decomposable code base. I think maybe UI code, or when you have complex business logic, there it's really easy for the LLM to kind of trick you and be like, yeah, I've implemented this, but it hasn't. It's just kind of made some test pass, but it hasn't actually understood what you want it to do. But here, a lot of it is just implementing a mathematical function, and that's much, much more easy to verify.
Yeah, again, a fascinating approach.
Yeah.
Interesting that great for you that it works so well with this particular use case, because I totally agree. I think distribution doesn't get enough credit for making products work. Why are you doing any of this? It's interesting. My guess is your brain enjoys the challenge. It's a better system in some ways, not all the time, but there's. What did you say at the start? There's a bunch of imperfect systems, and it's the best of a bad bunch, or something like that.
That sounds overly negative. Let's not repeat that. So yeah.
Right. Okay. Yeah. It was something along the lines of that. There's no coordinate system that's absolutely perfect.
Yeah, there's no perfect projection.
Yeah.
So in a way, each of them has got its own weakness.
Okay. Yeah. So with this, why are you doing this?
So the original motivation was that I stumbled across a tiling system in 2D with irregular pentagons. And I hadn't seen this before, and I'd often heard pentagons are the only shape that can't tile. And then when I saw this, it to me looks very much like a discrete grid system, and that makes sense. If I'm a developer of visualization software, then rather than walking down the road and admiring the beautiful architecture, I'm like, oh, that looks like H3 tiles, that looks like S2 tiles. It's just real fun at a party. This guy is just look, H3 on the wall. Yeah. So if you're a DGGS developer, everything looks like a grid system.
Yeah.
But I came across this tiling pattern, and I thought, wow, could this be actually made and extended over the whole globe? It turns out the answer is yes, and then it just really is quite fascinating because it goes down to very, very low level geometry. The way the indexing system in these grid systems work is often using something called a space filling curve. So you basically thread a line that passes through every cell on the globe exactly once. And that is how you define what the index is. So coming up with that is an interesting challenge in itself. And then, after some point, I was like, okay, I want to get this to a point where I can share this with people and sort of see what they think. And it definitely, I think people found it interesting. But then, as I was saying before, that's not enough to get people to use it. And I kind of thought, well, it's kind of a completely different but fascinating challenge to how can you get adoption? It's not just a maths problem, it's also a social, a people problem. How do you get people excited? How do you kind of do marketing, so to speak? It's kind of why I'm here now. I want people to listen to this, and I obviously enjoy the show, but hopefully afterwards go and take a look at the site and think oh, maybe I could use this for something, and maybe get involved or give some kind of feedback. So the motivation is kind of, I would say, altruistic or something. It's just because I found it very, very interesting, and it's a very deep rabbit hole that you can get into. But it also felt maybe one of the only projects that I've worked on where I felt I actually discovered something very, very fundamental. And then you think well, it's obviously interesting to work on tools or software that is useful to people. Like, having a job, there's nothing kind of wrong with that. But it's not so much a discovery, like kind of adding a button to a UI. It doesn't feel like you've stumbled across something new. And with this system, I haven't come across anyone who took this like tiling pattern and then applied it to a sphere. And I just thought, like, I don't know, this is what I can think of doing with this. Actually, like, funnily enough, I've had like a bunch of other ideas what this system could be used for. Like, you have geodesic domes in architecture. So I was thinking you could do the same thing with pentagons. Why not? In a fascinating way, then if you look at a golf ball, then not always, but very often the arrangement of the dots on a golf ball is the same as H3. If you look very closely, you see like hexagon patterns and pentagon ones. And actually on the A5 site, just as a bit of fun, I've made like a A5 golf ball. And at some point I was entertaining the idea of maybe I should, patent it and like go to some golf manufacturer. And like, no, seriously, it's just insane. Just stop.
Has anybody ever accused you of being a nerd?
Maybe.
Yeah. Yeah, I can imagine.
Yeah. Lovingly.
Of course. Yeah. I got to say, it's really refreshing to meet someone like you has the technical understanding first and foremost, sees the possibility here and follows through, not just have a great idea. I think there's lots of great ideas out in the world, but that understanding, it's not enough just to having a great idea. I need an ecosystem. I need to make it easy for people to use it. And dare I say it, I need to do some marketing around it. I need to have a great idea, make the tools, and then talk about it. And I think it's the ideas that spread. They're the ones that win. And you're doing a fantastic job. I think in a lot of ways you should be a role model for other people here at this conference that also have great ideas. I wish they would do more, not just have the great idea, but follow through with it, if you know what I mean. Not a critique of them. And I say this lovingly because I'd like to see more great ideas make it out into the world. So thanks very much for your efforts. I really appreciate it. I think this is cool. There'll be a bunch of links in the show notes. I really hope people check it out, and I hope they get in touch. Thanks for your time.
Happy to be here, and thanks a lot.